Introducing Harmonics and Fan Systems. I'm Scott Arnold, Senior Manager of Publications and Standards for Air Movement and Control Association International. On behalf of our more than 400 members worldwide, I want to thank you for joining us this afternoon. We realize there's a lot to see and do at the AHR Expo. We respect and value your time and hope you find this educational session well worth your while. The information contained in this session is provided by AMCA as an educational service. In making this educational activity available, AMCA is not endorsing, sponsoring, or recommending a particular company, product, or application. Lastly, this session is protected by U.S. and international copyright laws. Reproduction, distribution, display, and use of the material without written permission from AMCA International is prohibited. And with that, I'll introduce our presenter. Nicholas Popp is a standards and regulations research and development engineer with over 5 years of experience in the HVAC industry. Focused on ensuring product compliance with relevant industry standards, regulations, and quality requirements, he is actively involved with AMCA International and works closely with nationally recognized testing laboratories such as UL. He has a degree in mechanical engineering from the University of Central Oklahoma. Nicholas?
Thank you. So welcome. Thank you all for coming. So I like to say, working for a German company, beer is where a lot of business is conducted. Well, maybe one, maybe more. So I've included beer in this presentation, so I hope you stick around. So our learning objectives. So power quality, harmonics, and then solutions for harmonics for fan systems. So what is power quality? Power quality is the interaction between your distribution system, its customers, and the equipment manufacturers. This relationship is where you can make sure that you're having good power quality on different sides and how they work together in order to make sure your power is, optimal. So on the energy supply company side, they want to make sure that their power coming to the point of common coupling is of good quality. The plant operators want to follow protocols, regulations, standards to make sure that they are meeting requirements. This is, reducing harmonics, which we'll talk about later. And then on the equipment manufacturer side, they also want to make sure that their products are helping to, keep that power quality in good working condition. So things such as EMC interference emissions, EMC interference immunity. And so this relationship is where you're getting your power quality, and each can affect each other. So what is the importance of power quality? So a lot of times we're utilizing power electronics. These power electronics is what's helping to increase efficiency within your power grid and your system. But when you add those, you're adding stress to your grid and your system. So power electronics are rectifiers, inverters, VFDs, transformers, power semiconductors, etc. These are devices that are manipulating, changing, and controlling your power, your voltage. And with that, that's where comes the stress. So power quality has a lot of different topics, voltage dips, transients, unbalance, flicker, interruptions, different changes, and harmonics, which we'll get into a little bit later. So on the utility side, there's a few standards and regulations. IEEE 519, I'm sure you guys have heard of. This is what is used in North America. It's controlling your power quality at the point of common coupling, and it's talking about those power quality topics. Also, we have DIN EN 5160. This is used in Europe and other parts of the world, still mentioning and holding, trying to provide a good power quality. And this is all on the utility side. So IEEE 519, what it's doing is it's regulating the harmonics within your system. It's defining current distortions as TDD, or total demand distortion. And it's defining your voltage distortion as THDV, total harmonic distortion voltage. But it's not limiting your total harmonic distortion current of single components. So it's looking at your system as a whole. And then DIN EN 5160 is similar. It's regulating the power quality of low voltage, medium, and high voltage systems. Still looking at your power quality. Just threw that in there. I know most of us are probably looking at IEEE 519. And then we have some regulations and standards on the equipment manufacturer side. So we have IEC 61000-6-2 and -6-3, which is the interference immunity for industrial environments and interference emission for household environments. And then we also have IEC 61000-3-2 and -3-12, which is for low voltage equipment rated at current of 16 amps and below, as well as 16 amps and above to 75 amps. So we're looking at IEC 61000-6-2. This is for your industrial environments. Immunity is where it's saying it wants to prevent that any other equipment, anything else on your grid is affecting this device or this equipment. It's looking at ranges from 0 hertz to 400 gigahertz. And it's still looking at your power quality, making sure that you're looking at your transients, your dips, your voltage, and harmonics. And then 61000-6-3 is looking at the residential side. This is your emissions, so what is being emitted out to your site and your system. It is also up to a frequency of 400 gigahertz and looking at specific power quality requirements. Then when we look at 3-2 and 3-12, we're looking at the limits of harmonic load on equipment less than 16 amps and greater than 60 amps, below 75 amps. And I pulled out this table, which is, it's stating your limits for Class A equipment. So you're seeing your odd harmonics and your even harmonics and what your limits of harmonic current you can have for each of those currents, or those harmonic currents. So we'll get into harmonics and orders a little bit later. What are harmonics? Where do they come from? So harmonics are caused from nonlinear loads. So these are loads that are taking a sinusoidal wave and converting it, manipulating it. This is coming from LED lamps, power electronics like we just discussed in the beginning, computers, EC motors, frequency inverters. And so you can see the red graph is showing your current, and with that distortion, now we're seeing that your blue curve, which is your voltage, is now becoming distorted. So these nonlinear loads is what is causing the harmonics. This is where it's coming from, when you're manipulating your voltage, your sinusoidal wave. So we can look at a simple VFD or EC motor. There's 3 typical components. You have your rectifier, your DC link, and your IGBT power module. In your rectifier, you're taking in your sinusoidal voltage wave. You're converting it to a DC voltage, so cutting it, and so now you have a linear voltage, but it has some humps, some dips. And so with that, it goes into your DC link, and now you're trying to reduce all of those ripples and make it as linear as possible. Then you take your DC voltage, and now it's going into your IGBT power module. This is sending out a PWM, pulse width modulation signal, and now you're converting it back into a similar AC sinusoidal wave. And so when you're doing this, you're changing your voltage, and with that, you see distortion and thus harmonics. With your current distortion, you can then start to see distortion within your voltage, and that's when you start to have problems. So when we look a little bit deeper into the math behind harmonics, of what harmonics are, we're looking at Fourier series. So we have our fundamental wave, which is our perfect ideal sinusoidal wave. Here I'm looking at 50 hertz, which is common for Europe. Here we have 60 hertz. And then your harmonics and your harmonic orders, like it was showing in that table earlier, these are a multiple of that frequency that you're looking at. So if we're looking at 50 hertz, we have 100, we have 150, 200, and so on. Ideally, you would just want to see your fundamental wave, this perfect ideal sinusoidal wave. But when you have all of these nonlinear loads, your power electronics, this is where you're starting to see the harmonics, the different frequencies. When you add all of these together with the fundamental wave, this is where you get your distorted wave. So the green is good, and then all of the red bars are the harmonics, the things that you would want to mitigate, get rid of, reduce. So why do we care about harmonics? So harmonics can do a lot of different things, and I think it's relatively new that we've figured out about harmonics, that we're learning more about harmonics and what they can do. Usually you see higher temperatures within your motors, generators, your transformers. You're seeing fuses blown. You're seeing circuit breakers trips. You're seeing different equipment on your site that's just not working properly. It's not working efficiently. And you're seeing, with that current distortion, now voltage distortion. And this is the graph and curve that we were talking about before. But we're also looking at additional stress in our power systems. So I was talking about beer before, earlier in the presentation. So a lot of people like to talk about the power systems in relationship to beer because it's a little bit easier to understand. So we're looking at our P1. This is our active power. This is like the beer in your glass. This is what you're drinking, what you can use, right? Then you have your Q1, which is your reactive power. This is like the foam of the beer, and you don't want a lot of foam in your beer. And then you have your S1, is your parent power. This is the total power. So this relationship is what's giving you your power factor. So how efficient your system is running. And when you add harmonics to your system, it's like adding more foam. So now you have less beer. We don't want that. So yeah, this is the stress that's put on your power grid. So what can be done? On the equipment side, we can look at different filtration options, and we'll get into that a little bit later. On the design side of your grid, we can look at the ratio of our short circuit current and our load current, which this is where IEEE 519 comes in place. So what it's saying is this ratio, the bigger ratio you have, the less impedance you have, so the less stress you have on your grid. So here, this graph here, we can see that a higher ratio means we can have a higher total demand distortion. So this is your total grid. It's not necessarily looking at one component of the grid, it's looking at the total grid. So in the design stage, you can then look at, okay, I need more TDD, I need a greater ratio. So I wanted to explain a little bit more about TDD, THDI, THDV, kind of what they are, how they, what relationship they have, because I think there's a lot of confusion with it, especially with IEEE 519. So THDI is your total harmonic distortion. This is how much your current is deviating from that fundamental wave, which we were talking about in Fourier series. And so it's the measured harmonic current in ratio to your fundamental current. And here you can see the relationship where you have all your harmonic currents added together in ratio to your fundamental current. When we look at THDU or V, we use V in America, but in Europe we use U. This is your total harmonic distortion voltage. So similar, it's indicating your voltage and how much it's deviating from your fundamental voltage. And this is the ratio of your measured harmonic voltage to your fundamental first order. Similar formula, but now we're looking at voltage instead of harmonics. And then we have TDD, our total demand distortion. So this is the ratio of your measured harmonics up to the 50th order. Typically, we're looking at the 50th order. There's cases where you'll see harmonics at a greater order, but usually you can get majority of that information from the 50th order, to the full load fundamental current, which is usually looking at a 12-month period and what your average of that current is, right? So your full load, the total on your system. And so you can see that this formula looks very similar to THDI, but now we're looking at a different ratio with the full load current. So we can compare TDD, total demand distortion, with our total harmonic distortion current. So in a full load situation, these would be the same. But when you start looking at partial loads, this is when they start to differ, because we're looking at the ratio of the fundamental current versus the ratio at the full load current. And we can look at an example. So here we're looking at our THDI, TDD, and then you have your load, your current load, your fundamental current, and then your harmonics current. At full load, we can see that your THDI and your TDD are the same. As you go to a partial load, though, you are now seeing that the total harmonic distortion current is increasing in percentage, but your total demand distortion is decreasing. This is because the ratio of current is different, right? So your total harmonic distortion current, you're seeing an increase in percentage, but that's not actually an increase of harmonic currents that you're seeing. The total demand distortion is showing how much total harmonic current you're seeing on the system, which is actually decreasing because the amount of current on your system as you lower the load is less. You have less harmonic load. But the percentages is where you're seeing the difference. Hopefully this is making sense. So for the red, you're saying, okay, 0.65 harmonic amps is with the ratio of your fundamental current. So this is your 1.45. This is why you're seeing a almost 45% THDI. If we look at the 8.43, then we're seeing the ratio of our full fundamental harmonics, which is 7.71 to the 0.65. So this is why you're seeing that ratio difference. And this is why it's important with IEEE 519. It's not talking about a single device or component or part of your system. It's looking at the total system. So now we can start to look at the equipment manufacturer side and look at what solutions there are for harmonics within fan systems. So we have a few solutions. We have passive filters, active filters, which are external and internal. And then we can combine these options as well. So passive filters, these typically a very simple, easy plug-and-play solution. There's no additional really work except for installing it into your system, right? There's no calibration, you just plug it in. It's acting like a low-pass filter. So it's cutting out those higher harmonics, and thus it's reducing our total harmonic distortion current. So typically we see 7 to 20% of THDI with fan systems with the use of a passive filter. And with this, we are able to reduce the harmonic load on our electrical system. So we did some laboratory condition testing. So some examples, we have manufacturer one of a passive filter utilized with a 6-fan array. On the left, we're looking at our total power percentage versus our percentage value of THDI and THDV. We can see our THDV is 0, but we have THDI less than 10%. So this is pretty good. You can see that it's starting to increase a little bit in THDI as you go into a lower partial load. But what's really important is on the right, we're looking at our true power factor. This is the efficiency of your system, efficiency of your fans. And you can see that at 100% load, you're not quite hitting that 1. So you have more foam in your cup, right? Which is not ideal. And then as you decrease further partial loads, you start to see a dip. So this is not really helping with your power factor. It's just reducing that THDI. It's not really increasing any efficiency within your system. We can look at another manufacturer, and now we notice there's a drastic difference. Now, at partial load, we can see our total harmonic distortion current has increased above 15% at a partial load. But our true power factor at 100% load is now closer to that 1. So maybe this is a good solution for a system that's running at 100% load. Your THDI is still less than 10%. Your true power factor is close to that 1. So this might be a good solution. So passive filters are really good, but they have different interactions with different equipment. They have different solutions, different sites are different in how they work with the passive filter, and if the power quality is already struggling in other areas, or if there's other nonlinear loads affecting your system, it might lead to different results. And then we can look at a third manufacturer, and so we can see the power factors fairly similar. It's 1 at 100% or close to that 1, and it starts dipping. But then on the left side, we see an interesting dip at around 38% power. And then as it goes to less than 20%, it's increasing above that 15%. So really looking at your total site, your unit, how your equipment is working with that passive filter is important. Each passive filter is kind of leading to a different result. So now we can talk about active filters. So active filters, what they're doing is they're using sensing technology where they're looking at your current, they're looking at your voltage, they're monitoring this, and then they're creating a sinusoidal wave, a counteractive wave to the harmonics that it's seeing. And then with this, you're actually effectively canceling out those harmonics. So you're actually looking at what harmonics are on the site, on your grid, and you're removing them or canceling them out. With this, you do have to calibrate the filter. You have to look at each site and maybe figure out what is better for one site versus another site. But it's an optimal solution. It's a flexible solution because maybe your site is changing over time as well as you add more nonlinear loads to that site. Typically, we can see the THDI reduction to 5 to 15%. And here in the active filter, we're actually increasing the power factor close to that 0.99. So this is increasing energy savings and saving you money, increasing efficiency. And it's also reducing your harmonic load on the electrical system. So an example, laboratory conditions, again, we can see a before and after. So this is a 6-fan array and then a 6-fan array with the external active filter. On the left side, you can see that the THDI, total harmonic distortion current, is close to 35%, and then it starts to gradually increase in percentage as the load decreases. And you can see your power factor is not quite close to that 1. But then with the external active filter, we're able to reduce it significantly, and we're able to increase that power factor close to the 1 for a large portion of the power percentage. We can look at that closer here. So we're actually reducing the total harmonic distortion current less than 10% for the entire power percentage. And for a majority of the power percentage, you're seeing that that power factor is close to the 1. So this is increasing your efficiency and saving you money. And now we can look at an internal PFC, power factor correction. So unlike the passive filter and the active filter, this is all housed inside your motor or your VFD. So it's different in the sense of you have no extra wiring, you don't have to find space inside your cabinet, it's just already built within your motor. So we have the example we talked about earlier with the rectifier, the DC link, and the IGBT power module. Now we're looking at the rectifier becoming an active PFC. So this is a series of switches that is helping bring in a more ideal sinusoidal wave to the fan, and thus helping reduce your harmonics. And we can look at an example under laboratory conditions, 600 to 6,000 watts. We can see that the total harmonic distortion current is now less than 4% for the entire 600 to 6,000 power range. And we can see that the power factor is fairly close to that 1 for a majority of that range. And now we can see, okay, maybe we need to have a combination of these. So an active or passive harmonic filter utilized with fans that have the integrated PFC. So here we have laboratory conditions. We can see that at 80% or higher of the power percentage, we can see the total harmonic distortion current is 0, close to 0. And then it starts to slowly increase as it's going to a lower partial load, but it's still less than the 5% or even less than 4%. And you can see that your power factor is increased close to that 1. So this is a really optimal solution where you can get the best results, where you're utilizing the fans so they're not emitting any harmonics, they're not causing any problems, but then you're also using your external filter to help increase the power factor and reduce harmonic loads maybe on the system that's already existing. So now we can look at a comparison. So we have passive harmonic filters, which reduce your total harmonic distortion current They're suitable for IEEE 519. They're not increasing your power factor, and they're not necessarily flexible as your site and your grid is changing, the equipment's changing, harmonic loads are changing, and they're not really correcting your mains on balance, but they're a suitable solution in certain situations. And then we have our active harmonic filter solution, which is maybe your most flexible solution because it can be calibrated for different sites, different systems, different things that are happening, changes over years. It's suitable for IEEE 519. It's increasing your power factor. It's a flexible solution, obviously, and it's correcting your mains on balance. And then you have the simple solution. So your active PFC EC fan. So no additional wiring, no additional space within your cabinet. It's reducing your total harmonic distortion and it's increasing your power factors. So this might be a good solution for a system that doesn't have any power quality issues. There's no harmonics that are on the system or coming power quality issues. It's just you don't want to add anything to the system. And then maybe for a solution for a critical system would be using a combination, the active harmonic filter, external and internal. So here we can see that the total harmonic distortion can be reduced to less than 2% in laboratory conditions. We can see that it's suitable for IEEE 519. We know that the power factor is increasing. It's a flexible adjustment solution because that active harmonic filter can be calibrated to your system, and it's correcting your mains on balance. So to conclude, we know that power quality plays a crucial role in our overall health of our system. We know that harmonics can lead to issues and problems within our site, and to prevent these unwanted harmonics, we can utilize different passive, active, or combination of the two filters to reduce that harmonic load on our power system, our power supply. Any questions, comments, thoughts? Yes?
I've got one question. Where does this energy come from if you are talking about the active filter? So you have to add something in order to have a better sinusoidal solution. Where does this energy come from?
Yeah, so the filter is connected at the point of, so you have your fan system and then you connect your active filter before that fan system, and it's connected to your power supply and it's reading the power supply and it's monitoring your current and your voltage, and it's utilizing that to create a counteractive curve or counteractive sinusoidal wave that's counteracting the harmonics, right? So it's still connected to your power supply, your power system, and it's utilizing that, it's monitoring it, right? Yeah.
So, like one question that comes up is, you're selling these fans to customers, right? But you don't know what their power quality is necessarily as you're selling these.
Mm-hmm.
So how is it that I'm thinking about just like remote support, right, for these customers, and it seems like they have a power quality issue without having is the only way to figure out what kind of filtering you need to have support on site, taking these measurements, collecting this data?
Yeah, a lot of times you don't know necessarily if you have power quality issues until you go on site, you use a power analyzer, and then you can really define, okay, yeah, we have a harmonic issue, and with the power analyzer, you can really dial in, okay, where you're seeing that maybe from, and then that's where the active filter is really a good solution, because now you can use that power analyzer. You're knowing the active filter almost acts like a power analyzer, right? It's analyzing it. It's showing which orders, from the Fourier series that you're seeing those harmonics, and then you're able to combat those with the active filter. Power analyzer, you're just able to say, okay, I do have harmonics on my system. But yeah, typically, you're selling fans, you won't hear about anything until there is an issue, and then it's, okay, how do we determine if it is? And a lot of times I think customers will just do power analysis on the site, or maybe their customers want to do a site analysis, so sometimes they've already done something and you can ask, okay, do you have something? And from that, you can maybe determine, okay, there was already power quality issues, or my fans or something else being added is causing those power quality issues. Yeah.
Can harmonics from the power supply induce torsional vibration of the shaft?
Can harmonics cause vibrations?
Torsional vibration.
Torsional vibrations. I'm not 100% sure on that. If you send me an email, I can look into that and give you some feedback. Yeah.
So, similar question. Is there, do these power professionals give examples of where they might implement or how does this impact the system? How would I know? Is it consume too much energy? Bill's too high? Something's not working right?
Yeah, I mean, harmonics are kind of tricky because they're not always the same. You know, in one site you might see one thing, in another site you might see a different thing. So that's where I think, the last 10, 15 years we really started investigating harmonics more, and we're starting to learn more. A lot of times you see equipment that's just not running as efficient as it should be. It's running hotter, so you're seeing over temperatures. This is where you're seeing fuses and circuit breakers trip. And just like equipment's running functionally, you can see lights flicker. I mean, there's signs that you can kind of look at, but a lot of times each site can be slightly different or completely different. So it's definitely something I think the industry's still working on learning more about. Yes?
At what point do you feel like internal power factor correction just becomes the industry standard on certain equipment? Because like me on the MEP consulting side, right? Like we're dealing with a job right now where they went in, they put in these 4 huge shredder motors, and then we get a call and they're like, hey, can y'all get involved with this? We need to put these, we're being recommended to put these huge active filters out there, which is an extremely expensive solution for this site because now we have to build a building to house these things because there's not, physical space on site. We have to cool and ventilate the space, and these things are huge because they have, obviously op amps on them that have to overcome these huge horsepower DC motors. It seems like on the floor today, it seems like ABB's kind of getting ahead of the curve on this, or starting to integrate with Aeon and some others, but like at large, it doesn't seem like the motors and or HVAC industry is really doing internal power factor correction at the drives. But obviously VFDs is pretty much the standard across the industry now, just in the name of, efficiency of operation and lowering electrical costs. So like at what point is the industry, does it seem to be moving towards having motor drives and actually solving things, internally at each individual inverter or VFD or whatever?
That's a really good question. I mean, I would say there's definitely an increase in demand in harmonic filtration in total. I see it is really dependent on the site. I think newer sites where they can really design the grid to handle what they're putting on it, is the best result, where you design the grid to handle this much harmonic load, this amount of total demand distortion, but when you're retrofitting, you're adding more nonlinear loads to your system. This is when you're starting to see, okay, the harmonics are increasing so much that we're seeing site problems. So I don't know if it would be like a complete, this is the only solution, because in a lot of cases, maybe your site can handle that percentage of harmonic distortion as long as it's current and not voltage. It's when it starts to move from a little bit of current distortion to your voltage distortion that you're seeing problems. I definitely see a move to, okay, we need filter options. The thing with internal PFC is that it's not helping with your site. So it's really just, I'm reducing the harmonics that my fan or my motor is outputting, right? But if your site already has issues, there's another VFD that's not filtered, there's other equipment that's not filtered, whatever else there is, and it's causing issues on your site, then that internal PFC is not helping. So this is where the external active filter comes into play. It's able to look at your site as a whole and help correct that power quality. So I think it's really a case-by-case situation. I think filtration in a total is definitely going to start coming up a lot more and be maybe spec'd in more jobs. And I think maybe even like John was saying, that we have more power analysis on sites so we know what we're coming up against, right? What's already there, and are we adding too much? Do we need to mitigate what's already there, or do we just need to not add as much to the system? Okay? Yeah, thank you guys.